Good morning or good afternoon, everyone, depending on where you're calling from. My name is Charla, and I want to welcome you to today's webinar, New Opportunities for Simplified Stream Processing with Hazelcast Jet 4.0. Before we begin, we do have a couple of housekeeping items to go over. Everyone will be muted for the webinar, so please type any questions you may have as we go along in the Q&A panel, and we'll try and answer as many as we can at the end of the presentation. Also, this webinar session is being recorded, and it will be sent out to everyone via email following the webinar. Now that we've taken care of that, I want to thank you all again for taking the time out of your day to join us for today's webinar, presented by Dale Kim and Joe Shorwin. Dale Kim is the Senior Director of Technical Solutions at Hazelcast, and is responsible for product and go-to-market strategy for the in-memory computing platform. His background includes technical and management roles at IT companies in areas such as relational databases, search, content management, NoSQL, Hadoop Spark, and big data analytics. Dale holds an MBA from Santa Clara and a BA in computer science from Berkeley. He will be joined today by Joe Sherwin. Joe is a senior-level solution architect at Hazelcast with 22 years of experience in the design, development, and implementation of application systems with multi-tiered distributed computing environments. He has experience architecting and implementing solutions using COBRA, RMI, Java EE compliant distributed object architectures, in-memory high transaction, low latency solutions using Hazelcast IMDG, Gemfire, Encache, and Oracle Coherence, and solutions deployable on platforms like Cloud Foundry, Amazon Web Services, Rackspace, or Heroku. And with that, I'm going to pass it off to Dale to get us started.
Great. Thank you, Charla. So hello, everyone. Again, this is Dale Kim of Hazelcast, and these are the topics that we'd like to share with you as part of this webinar. So I know that some of you may not be a current Hazelcast customer and are looking to explore and learn more about what we provide. So I'll give a brief overview of Hazelcast Jet so you get a sense of where that might fit into your data architecture. And then we'll spend the bulk of the time talking about Hazelcast Jet 4.0 and a lot of the new key features. And the three features we want to talk about are the user-defined functions that enable you to run Python within a Jet pipeline, the new change in data capture integration that adds more capabilities around capturing the transaction log data from things like databases, and then exactly once processing for more types of sources and syncs. And keep in mind that Hazelcast Jet and Hazelcast IMDG are open source products, so you can get started right away. If you go to the site hazelcast.org, you can download the products, and they come in a relatively small jar file, so it's very easy to embed in your applications or run as a client-server model. So you're welcome to take a look at that. And I want to mention that all the things that we're talking about today are available in the open source edition. So these capabilities, as well as some of the additional features we'll talk about, are available in 4.0. There is one capability I will talk about that is in our commercial version of Hazelcast Jet. And it's not a new feature in 4.0. It's an existing feature, but it's relevant to one of the capabilities in 4.0. So I want to call that out, and I'll make sure I'll let you know what feature that is, and that the fact that it is part of our commercial product versus the open source product. There are a couple other features that we'll go over, and then I'll try to be fairly high level and fairly concise about my descriptions of these capabilities. And if I am too brief in my descriptions, I'll have Joe jump in and add a little bit more elaboration so that you get a full sense of the picture around these capabilities. And of course, if something's not clear, then please be sure to type your question into the Q&A box that you should have on your webinar. And then I'll hand it over to Joe for a few minutes, and he'll go through some code and walk through an example of how you would run the Python code within the context of a Jet pipeline. And in fact, he'll go into a bit more deep detail for code, and along the way, we'll show some code examples. So for those of you who aren't coders, I think in some sense it might be still interesting listening to the steps and so you get a better understanding of what's going on behind the covers. And the walkthrough will go through a little bit more detail than you're used to seeing, but hopefully it'll be interesting to you non-coders. And then, as we said, we'll have the Q&A at the very end. So let's go ahead and get started with a quick overview. So I just want to spend a few minutes talking about this. And this is the standard data flow diagram that you've seen in other technologies where you have all the sources on the left. You have the core technology in the middle, represented by that big blue box. And then you have the target destinations, or in this case, sinks, on the far right. And so the connectivity to the sources and the sinks are performed with connectors. So we have a suite of modules that allow you to connect to most of the popular data platforms out there. So it gives you that standardized and pre-built connectivity into these sources and sinks. And of course, we have an API that you can use to build connectivity to any of your more unique data platforms. But most of the popular data platforms out there will be covered by the Jet and IMDG connectors that we provide. And based on some capabilities that we've added in 4.0, we'll probably get a more complete picture around what you can integrate with. So we'll talk a little bit more about that. But if you look at the middle box, then you'll see that Jet is all about processing data in a series of subtasks or steps that's best represented by a directed acyclic graph, or a DAG. So you've probably heard about DAGs in other contexts, and we use DAGs as a means for optimization and planning of the jobs. So we can break apart an entire job into its steps as defined by the declarative API that we provide, the pipeline API. And the Jet will automatically specify where there's opportunities for parallelism and take advantage of all the available cores within your cluster so that you can have optimal performance. So Jet is all about low latency and high throughput, and so we've very much optimized around that. And so a lot of what we're talking about as part of this webinar includes additional capabilities that build on top of that performance advantage that we've built in the past. And so you'll see the IMDG at the bottom left, which is a core part of any stream processing environment, or at least the functionality is. So if you think about stream processing, oftentimes it requires data lookups or enrichment of that streaming data, because the streaming data is often fairly sparse, so there's not a lot of duplication of data across the different data elements that are in the stream. And so you want some means of looking up data and enriching the stream. So IMDG is tightly integrated to enable that. And then the bottom right, we'll be talking a bit more, but that's an example of where you can plug in outside code as part of an ML, machine learning inference capability and subtask within Jet. So let me talk about the integration and how that's unique in the market. So if you think about how a stream processing architecture looks like, you have your stream processing engine itself, and then there's ecosystem around it to help support it. So oftentimes this can be fairly complex. And if you have a lot of experience of this, you probably don't think about complexity at all. But when you consider that you also have to have an external data store, again, for that stream enrichment, you have to bolt that on, and there's some latency and complexity associated with that store as well. So you've got these two disparate components that you need to tie together. And the challenges are pretty straightforward. They're about latency. It's about the additional integration work and the maintenance and the high availability associated with these two systems. And so how do you manage all that? It takes a lot of effort, and a lot of times latency is the key challenge, where if you have a high-speed system and you want to be able to do more within the same amount of processing time as defined by a service level agreement, then you want to make sure that you have the extra performance headroom to be able to do that extra work. And so contrast that to how Hazelcast looks, where we have the stream processor and that quote-unquote external lookup system built in, and Hazelcast IMDG as a tightly integrated in-memory store. You get a lot of the advantages around having that built into the stream processing framework, so that there's low latency and high throughput, so all the performance advantages that you need. And one thing I like calling out is that Intel Optane/Rambox. So one of the great things about the Intel Optane DC persistent memory technology that was released a few years ago is that not only does it provide that persistent memory, the non-volatile storage that you would expect from the name, but it also provides volatile memory capability. So it looks very much like RAM in that volatile mode. So you can use Intel Optane as an alternative to RAM. It's just as fast in many cases, but about half the price. So if the price of memory and in-memory capabilities has been an inhibitor for you in the past, that's a great opportunity for being able to take advantage of that level of speed and using Hazelcast to take advantage of that memory. So that's all I want to talk about so far about Hazelcast Jet in general. So let's jump over to 4.0 capabilities. And as I mentioned, these are the three capabilities I wanted to talk about. So let's first talk about user-defined functions. And so for 4.0, we've added user-defined functions as first-class tasks. And what that means is that we have the infrastructure that'll let you run non-native code or native Python code, but not non-Java code within your pipeline. So keeping in mind that Jet is based on Java code, the question was, how do you integrate Python code as part of that in a seamless way? And so what happens here is that we have a provision where Jet will manage the external Python VMs and run them on the same nodes as the processing tasks. So you don't have the latency of reaching across the network to some separate cluster. They are instantiated. The VMs are instantiated on the same nodes, and so that you get a lot of performance benefits there. And there's an element of simplicity here where Jet will maintain those Python VMs. So they'll start them up, they'll restart them if there's any node or VM failure. And you don't have to worry about a lot of the intricacies of managing two separate systems, the Jet pipeline or the Python VMs separately. So all of this is handled for you to make it simpler, and ultimately is also about providing that high performance for some of the capabilities that we provide. So just looking quickly at the diagram, you see on the left the Jet JVM. There's the source and then the core processing by Jet, and then there's the sink where the information is sent out. And then using gRPC, where we're talking to the Python VMs and the tasks defined and that are running within those VMs. And one of the things that we add to this is the batching of requests so that we get additional performance from those Python VMs, in addition to the parallelism that we can provide. So a lot of opportunities for optimization that we've taken advantage of so that we get the performance that you normally wouldn't see in a Python-based infrastructure. Let me just walk through the example code really quickly, and I think this is going to be pretty straightforward for most of you. So if you look at the Jet pipeline code, you start off by simply instantiating the pipeline, and then the next line you have a read from, and what that's basically saying is, first of all, read from a file, which is in the test sources class, and then that will be presented as an array of numbers. Then if you jump down to the apply line, the fourth line down, we're calling the map using Python method and setting up the configuration for the Python code. So that next line, set base dir, points to the directory where your Python code lives. So that's the way that you package the Python code as part of your pipeline. You simply create a directory, put your code in there, and then you specify here. And then the next line that takes square root is the Python code file name itself. So you point to that, and then you've got the base directory, you got the file, and then you're mostly good to go. One thing that we didn't include in this example is another method, the set handler function, which I believe Joe will talk about. And that's the actual function within the code, the Python code that you can specify. So obviously you can have multiple functions within that file. And if you don't specify that function, then the default function within that file and within the handler module is transform_list, as you can see in that Python function below. So that's all it takes in terms of pointing to the Python code as part of a Jet pipeline. You can do all the processing in Java at very high speed, But if you have code in Python you want to run as that user-defined function, you can easily plug it in. And so now I just want to give an example of some of the performance characteristics when you compare running within the context of Jet versus, or in this user-defined function framework versus running over REST. And so we were using the scikit-learn library here, and certainly your mileage will vary depending on the Python libraries that you're using. But we did some simple tests, just get a rough ballpark in terms of the performance differences. And so as part of a pipeline, if we call out to a REST environment that's running a scikit-learn algorithm, we were seeing about 5 operations per second. And this was without the parallelism that some other libraries might perform. So with some of the capabilities and REST infrastructure that other libraries provide, you're going to get performance improvements over the 5 operations per second, but we want to just use that as one example of a baseline. And what's more important, even if you don't look at the basic REST numbers, Jet with no parallelism on this single node, this 4-core node, you get over 20,000 operations per second. And then when we take advantage of all the cores, we were seeing 97,000 operations per second. So hopefully that gives you a sense of the performance improvements that are done as a result of the parallelism, as well as the data pipelining or the batching of data that are sent to the Python code and for processing. So great performance there. And again, the reliability and maintenance, the self-maintenance is an important part of this deployment model. So let me talk about rapid job upgrade. And this is the one capability that I mentioned earlier that is part of our enterprise version, our commercial version. So rapid job upgrade is simply a mechanism for being able to swap out existing code with new code for a given job very seamlessly, so that there's no data loss, there's no duplication, and you can very easily upgrade any job that you have running with your updated code. And so when you use this job upgrade capability, this is an example here in the diagram where you have potentially 2 jobs running, and then you submit the newer version of job 1, and then that gets quickly replaced as a result of snapshots that are being run on Hazelcast Jet. So it keeps track of where the streaming data is. Then I'll swap in the new job and then continue from there. So again, no data loss, no data points are missed, and there's no duplication. And so one of the ideal use cases for having this Python user-defined function is, of course, machine learning. And so specifically the machine learning inference side of the machine learning world. So we can now add Python code as a first-class citizen within Hazelcast. And if you're familiar with deploying machine learning into production, or this notion of machine learning inference, that often is a very much of a challenge for a number of reasons, one of which is what we call the impedance mismatch between data scientists and data engineers in terms of what they think about, what are the priorities. So from a data scientist perspective, they'll create data models, do a number of experiments, do some testing, validation, of course the training, and then they want to hand it off to a data engineer who will plug it into production. But the data engineer doesn't simply think of what value the code brings. They have to think about the packaging, the deployment model, how to scale, how to maintain, what's the life cycle for updating the models, the retraining. So a lot to think about, and they don't necessarily speak the same quote-unquote language. So how do you simplify the process in getting a ready-to-run model into a production environment? So there's definitely a separation of concerns methodology in place, where if you can simplify the means of deploying Python code into the Jet pipeline, then that will increase the percentage of models that can be deployed into production. So again, this is about speed. This is about not having to add additional work. Like a lot of times companies will take their Python code and then convert it to Java. So there's an extra delay there in trying to get that done, more opportunities for introducing bugs. And so if you can eliminate that, just run the Python code natively, it's definitely simplify your overall process. So at the bottom there, you see it's about throughput, latency, simplicity, and reliability. And I see that someone had asked a question. And someone asked about, if I can jump in and ask that question real quick, about the latency using Octane. And so for general purpose use of Octane as a volatile memory component, you'll see a little bit of degradation. So I've heard reports of around 10% degradation versus dynamic RAM. So it'll be close, but in a lot of tests that we've run where the data objects might be, say, under 1K that you're processing within our IMDG, the performance characteristics will be identical to dynamic RAM. So it depends on what type of data you're dealing with, but in many cases, we're seeing that Octane runs as fast as DRAM. So it's a great alternative to using the more expensive DRAM. And there was another question that'll hold up to the end about performance. And so I included this slide just for the sake of completeness. I mean, this was obvious based on my earlier commentary where you can run existing models that may be running inside of some REST provider or in some separate cluster and tie it in with Jet. So hopefully that's an obvious point. When I talked about the benchmark about testing with that REST environment, then this is what we're referring to. So most libraries do provide infrastructure for deploying the model itself, but doesn't necessarily have the mechanism for feeding real-time data or any type of infrastructure for feeding data into that REST model. And that's where Jet and IMDG can fit in, where we'll handle the pipeline of data and then dump it over to the REST model and get the score back and then proceed from there. So you won't get the performance that you can get from Jet. You will have a separate cluster or separate technologies that you have to maintain on your own. So if there is a node failure, then that's something that you have to account for. And that's why we saw a need around machine learning inference where a stream processing engine could absolutely help out in simplifying the overall process. All right, so let's talk about change data capture. And so for those of you who haven't done much with change data capture, in a way you can think of it as turning batch-oriented systems into a streaming-oriented system. And that's, hopefully none of you think of that as an oversimplification, but just one way to describe that. So if you think about all the transactions and operations that you might perform on a database, and think about all those operations in order, one at a time, that in a way looks like a stream. So you might change data elements, you might change data tables, and if you capture all of that, which is being done in the transaction log or relational databases, and read from that transaction log and then send that over the wire to some other destination, then you've got yourself that change data capture. And so because it looks like a stream, then of course stream processing engines are great technologies for being able to operate on them. And so if you think about what change data capture has mostly been about in the past, it's been about replication. So you have one database, run a bunch of operations, and you want to efficiently reflect those updates to some remote site so that you can have the two sites synced up together. And so change data capture was a great way of doing that. But certainly there are other great use cases for CDC as well. So let me just point out that we already had integration with a technology known as Stream to support Oracle, CDC on Oracle. And so new for 4.0 is an integration with the Debezium project, which gives us support for other databases. So no matter what database you're running, as listed here, any updates that are being made from applications or other systems will be reflected in that CDC log file or the log stream, and that'll be sent to Jet that will allow us to do processing on that. And so some of the use cases would include derived data views, and I think another way of describing that, which you guys will be familiar with, is materialized views. So if you think about the separation of the live perhaps OLTP system versus the analytics systems, then CDC is a great way of sending information to a processing engine that can index and format and transform that data into multiple materialized views that will serve different groups of end users. So you get a lot of flexibility there. And then any user behavior analytics can be done as a result of seeing each and every individual update to the database. So you have that granularity that you would expect from a stream, and you can perform analytics based on that information. And you can also use CDC to create a hot cache. So very similar to the notion of a materialized view, but making a cache in memory that's continually updated based on the operations that are being done on the underlying database. So another opportunity for using Jet and Hazelcast IMDG together for creating a high-speed analytics environment based on work that's being done on your operational database in an OLTP type of manner. The example code is pretty straightforward. If you look at the configuration at the top, this is all standard database connectivity stuff using the Debezium connector. And then when you run the Jet pipeline, you instantiate the pipeline, and then you'll see near the bottom the read from function that simply points to a Debezium source. And so just like any other connector, any other data source, you point to Debezium based on the configuration you've specified, and now you can do processing on that data. Okay. All right, so now let's jump to exactly once streaming transactions. Now, if you're familiar with exactly once processing and distributed transactions, you know that this is an extremely complex topic and there's a lot to it. Now, try to distill it fairly high level so that it makes sense for some of you folks that haven't really dug into this that much. And so the notion of exactly once processing sounds simple enough, where there's a data element coming from a stream, you process it, and then you send it out to some destination. And you want to make sure that there's continuity so that the data is only processed once. And that sounds obvious. And this is all about failure handling, so fault tolerance. So obviously, if a system's running well, then there aren't going to be any problems about exactly once processing. It's only when you encounter a failure within the context of node failures, or you encounter a network partition, then how you make sure that you can recover from that failed transaction without losing data or without duplicating any of the effort. And so, there's a lot of pieces that need to be included as part of this process to make sure it works. So in the past, Jet had the capabilities of handling exactly once processing, but it did rely on some requirements on the source side and the sink side. So there were some characteristics there. On the source side, it needed to be replayable, meaning that you could tell the system, I want to go back in time and look at earlier reads. So the system was maintaining an ordered log of the data that was being included in the stream. And so a technology like Apache Kafka is an example of a replayable source where you can go back to previous data elements if there's a failure so that you can take that and then try to rerun the transaction that might not have succeeded. And then on the sink side, you needed to have an idempotent source so that if there's no failure, then you can rewrite to that sink. And for those of you who aren't familiar with that term, idempotent simply means that if you take action on a set of data again and again, so you take action on it, and then for the output, take action on that again, you still get the same results. A perfect example of an idempotent function is multiplying by 1. So multiply any number by 1. If you take a number, multiply by 1, you get the same number. Multiply by 1 again, you get the same number, and on and on and on. And so what this is saying here is that if the write to the sink didn't succeed the first time because of failure, then you can write it again, and it won't create a new value. It'll if you use a sink that has upsert capabilities, then you'll make sure that you won't write it twice. But of course, if you have any triggers on your sync, like you're working with a relational database and you have a trigger, then it will look like two operations and it might call the trigger twice. And so that's an opportunity for being able to avoid that by using the distributed transaction mechanism that we've included in 4.0. So let me cover that a little bit. So the question here is, what if you don't have the replayable sources or the idempotent sinks? And so that's where we've incorporated distributed transaction logic so that you can use a non-replayable source or a non-idempotent sink. And so Jet will keep track of the reads, and that's managed as part of the snapshotting that it's doing for the sake of recovery. So it's tracking the different transaction IDs. Depending on what the replayable source is capable of, it'll handle it slightly differently, but ultimately, functionally, at the high level, it'll do the same behavior. It'll take the same behavior. And what I mean by that, to give an example, is if the source supports XA transactions where you can do a two-phase commit, then it'll take advantage of that. And we've seen that some of the implementations on some data platforms have been buggy, so we can't always rely on that to work in an exactly once paradigm. So we've put in this logic where if you have that XA transaction and it works, we'll take advantage of that as part of that two-phase commit. But if there is not an XA mechanism within the data platform, or we know it to be buggy, what we'll do is read the data and process it. And prior to acknowledging the read, we'll do the rest of the transaction. And only until we see a complete commit on all sides will we acknowledge the read from that data source. And then after we do the acknowledgement, that's when that data element might be discarded. So we want to make sure that we read the element and keep it live before we do an acknowledgement. So that's the logic that's included on the source side. And then on the sync side, we need to have very similar type of behavior where we need to keep track of the transactions in a two-phase like commit. I mean, we call it distributed transactions simply because of the different ways that could be implemented based on the different sources and syncs. But ultimately, what you're seeing is that two-phase commit to make sure that any data element that goes through the system and written out will be handled exactly once. Okay, and so for Jet 3.x, just to review this, some of the sources included Kafka and Hazelcast IMAPs, and the syncs were any store that supported upsert. So in 4.0, we added JMS. So any JMS provider can be used as a source. So again, we use that distributed transaction logic to make sure that there isn't that loss of data. And then syncs will include Kafka and any file. And if you think about it, why would Kafka be included as a sync? Well, in one sense, Kafka is often used as an intermediary between different tasks, between different jobs. So you might read from Kafka and then write back to Kafka and then have some other process reading from that topic as well. So you definitely want Kafka to participate in this type of transaction. And of course, Kafka doesn't have that mechanism for guaranteeing a write because the replayability is not the issue here. The issue is whether you get that acknowledgement that the write to Kafka was done correctly. And so this logic will help include Kafka as a sync as part of your pipeline. And then we'll be adding more sources and syncs in the future. And currently what we have planned for Jet 4.1 is including JMS and JDBC as syncs. And I mentioned earlier that JDBC or any upsert-ready source can be used. And this new capability in Jet 4.1 for JDBC addresses that issue around triggers that you might have in your database and making sure that you don't write or do an upsert that triggers a trigger a second time. Okay, let me quickly go through some of the additional features. And one other capability is this notion of being able to publish messages directly to the Jet caller. And that's implemented within observables class. you're essentially creating a new sync, which is a callback. And so now you can act immediately on that data without having to read it from a sync. So if you remember back to the data flow diagram where you had the sources writing out and then processing and then writing out to a sync, instead of dumping it to a sync where you will retrieve it from there, you can specify the callback right away. So if you look at the code here, there's another simple example where we've constructed an observable, and then we register it. And then you see in that second line, we add observer for that observable. And you'll see that we're just printing out to system out. And then we set up the pipeline and run it. And so any output that we get as a result of the processing will be written to that callback, which essentially means it'll be print line. Some other capabilities, including Twitter as a source. So we have a connector to Twitter, so you can use Twitter output as a feed into Jet and do processing on that. So that's pretty straightforward. And then Kafka Connect as a source. And what that means is, if you're familiar with Apache Kafka as a messaging bus, they provide a number of connectors as well to different sources and syncs. And what we've done is created a source module that can essentially emulate Kafka and use all the Kafka Connect modules as sources. So you don't have to set up a Kafka cluster for the purposes of being able to access all of the sources that are available to Kafka. We're basically taking advantage of what's out there and can connect to a wider variety of data sources. So as I mentioned earlier, there's an opportunity to connect to many different sources, and most of the sources that you would need are probably covered with a combination of Jet connectors, IMDG connectors, and Kafka Connect modules. But certainly you have the API in case you have a custom environment that you want to integrate. Okay, with that, let me hand it over to Joe, who will go through his code and give you an example of Jet in action.
Thank you, Dale. Hopefully everyone can see my screen. So what I'm going to demonstrate is an example of the ability to apply a Python function to a Jet pipeline. It's a very simple pipeline, but the overall goal of the 4.0 version of our product is simplification of machine learning inference. Dale spoke of running Java models, H2O, TensorFlow. So this Python runner allows you to run models that are written in Python, and the overall goal here is simplification. We simplify the development of data scientists, development team interaction by decoupling the concerns of the model development and the actual usage of the model in real time. So it should allow an easy workflow between the company's ML team and the development team as well. So what I'm taking here is the basic approach for the Python runner. Basically, what I'm doing in my code is specifying a directory, taking that directory that contains all my Python modules and replicating it on all the nodes in my Jet cluster. I'm doing this on the local machine, of course, and I'm only running one node at this point, but you get the point. So this, again, allows the Python code to be 100% Jet agnostic. So it has no awareness about Jet or any of our APIs. It's simply a function that you would normally, in the traditional manner, call with a REST API within your processing. In this case, I'm processing a file which has demographic information about someone's people, the age, work class, education, and I'm trying to get some statistics on this large file in a batch manner. So one of the things that Jet is able to do, not only is it able to do streaming sources, you can actually do batch sources here. The code, again, is very simple. There's a before step here, which simply sets up the Jet Bootstrap instance. And then there's the actual step here, which actually calls the Jet module. So here you can see in my pipeline, what we call a pipeline is what we're building, and we submit that to create a job. I'm using the API map using Python. I'm setting my base directory. I'm telling it which Python module to use. And as Dale mentioned, you can actually specify the function within the module. And also, you can set parallelism. So I could decide how many Python environments I'm running locally to multitask the calls to my handle function. So that again gives us the ability to greatly improve the performance over the RCP or normal REST calls. So once I pass the data set to the function, I'm just basically writing some log. The function itself will actually write files, which has the calculated statistics on the data set. So let's get to it. So basically, the first step here is MVM, Maven clean and package. The next step is to start a Jet node, and again, just go into the Jet install, Hazelcast Jet bin, and start the server. Started. So using my Java project, I'm going to submit this class as a Jet job. And basically, a Jet job is a POJO with a main, and it basically gets the static reference to the server that I'm actually submitting it to. So here's the call. So I'm basically calling this Jet script, passing the submit argument, and passing the jar to my project. So let's see what happens. One of the other things about this is that Jet will automatically download any required environments, any dependent Python code or anything like that to the local environment. So let's see if I do have that. Hold on, sorry. Do the Maven clean, sorry. All right, so there we go. All right, so here you can see my job is starting out. It's building my environment. Again, if this will happen automatically. Yeah, and again, I cleaned it just to make sure that we can see all the steps. So typically the startup time. So here you go, you can see it's running the inference and it's calling the handle and it's creating my results set. Okay. And it actually finished. So go to my output directory, and here I should see come on. So my means, yearly income, bachelor's, doctorate, high school grads, masters, some college. So that's basically how you actually would run a Python model. Now, some of the questions I think people have on their mind is, I don't know if anyone is familiar with GPRC. GPRC is what we're using to call into the Python environment. GPRC is a high performance RPC framework, which it's open source and a cross platform. With that, I hand it back to Dale.
Great. Thanks a lot, Joe. And so let me just wrap up by referring to a few resources that are available on our site. So I mentioned earlier our developer-oriented open source site, hazelcast.org, and you can read our blog on our .com site. So we talk about Jet 4.0, the capabilities that are released as part of this latest version. And that's written by Jan Genser, who's our lead on Jet from an engineering side. And then our product manager, Vladimir, wrote about machine learning inference at scale. So both very good blogs that give a great overview of some of these new capabilities. And of course, we have training available free on demand. So check out training.hazelcast.com to learn more about stream processing, which this course uses Jet as the example, obviously, to give you a sense of not only what Jet can do, but some of the things that you should be thinking about as part of your stream processing initiatives. Okay, with that, well, thank you very much for attending. With that, let's go into Q&A. And I think we had a question earlier about the Python performance versus Java performance as part of that machine learning inference capability. And Joe, did you want to comment on that?
Yeah, so what we've seen in our testing, we've seen the average latency for calling. I think you had that on your slide, Dale. Is about 90 nanoseconds with a max about 700 nanoseconds. And those tasks, those numbers do not include any kind of GC introduced hiccups. So it's much faster than what you would get if you were doing a REST-based call out to a Python Lambda, something like that that's running, maybe something that AWS provides.
Okay, great. Another question, how does Jet compare to other stream processors in terms of speed? So I think I can take a stab at this one. So we actually have some published benchmarks on Jet as compared to some of the other popular frameworks out there, including Flink, Apache Flink, and Apache Spark Streaming. And you'll see that we have significant performance improvements over them, not only in terms of throughput, but also in terms of latency. And obviously the key thing about latency is the percentage of responses that return within an acceptable time frame. So for any stream processing engine, certainly within the 80th percentile, you'll see good and similar performance across the different stream processing engines. It's once you start getting into the 90s and the 99th percentile of latencies where you really want to make sure that that's completely consistent, and that's where we really shine. So if you look at the characteristics of the others, once you start getting into those higher percentile, that's when the latency really starts to degrade, whereas we can maintain a relatively flat and consistent performance characteristic at those high percentile levels, which is obviously what you want as part of a production system. Anything you want to add to that, Joe?
No, that's correct. I just wanted to add some more details to my answer previously. Java performance is always going to be much better than calling out to a GPRC Python environment. And again, the other thing about the Java performance is that since creating multiple threads in Java and using all the CPU cores available is actually based on the JVM, so you can parallelize as much as you want. Parallelizing and creating multiple Python environments per Jet node, it's probably going to be a lot heavier than creating threads. So that's where you'll see some performance degradation when you're comparing calling out to Python versus writing your your pipeline completely in Java. Also, we plan on having in 4.1 is a similar capability for calling C++ module. So that should be interesting in terms of performance and compared to those two.
Okay, great. Thanks, Joe. And another question about testing Optane versus ScaleFlux 3D storage. I'm actually not familiar with ScaleFlux 3D. Joe, are you familiar with that?
Actually, no, I'm not. I'd be interested to research that. ScaleFlux 3D storage. I assume it's a similar technology, but I don't know any specifics about it.
Yeah, so the person who asked that question, if you can add some pointers to where we can look into that, and that might be able to help us to see what kind of performance characteristics you might see. So yeah, as of now, no performance tests there.
Yeah, and one of the things I want to point out with this Optane or any other secondary storage capability, it's the key here is to make the environments, the return on investments a lot better as far as the cost of DRAM and or how dense you can put, how much memory you can put, how much DRAM you can put in a machine, whether you're speccing that machine on a cloud provider or on-prem. So it's really the return on investment, the large data set that you might be doing your ML or AI applications against, and making it that more of a financially plausible solution.
Okay, thanks, Joe. Another question, which we seem to get a good amount. Is Jet an alternative to Kafka? You want to take that one, Joe?
Yeah. So Kafka has Kafka Streams, and Kafka Streams is different than Kafka messaging. Jet provides connectors to Kafka, so we work very well with Kafka as a data source, also as a data sink. So we can transform, analyze data with the auto-scalable Jet environment and read from Kafka and write to Kafka as well. So Kafka messaging is first class in terms of messaging and having a bus that you can communicate to multiple different systems, your result set. As far as compute, I think the way we actually compare to Kafka Streams is quite favorably in terms of, because again, Kafka Streams relies on a lot of broker creations, and it does require a more robust Kafka environment. So Jet actually makes it a lot easier to scale, and of course our performance will be multiples better than Kafka Streams.
Okay, great.
The other component of Jet is that the ability to store data in memory. So if you have reference data you want to store locally in memory in the Jet grid, that also makes your job processing a lot faster, multiple times. I don't know, Dale, if you have the comparison graph that we've done with testing in Jet, but you'll see once you store data in memory, we flat out beat any other solution.
Okay, great. Question. You talk about inference, but can Jet be used for machine learning training? And if I can throw in my thoughts on that. So if simplicity is one of the key benefits of leveraging Jet and Hazelcast, then a lot of the focus that we're working on is on the inference side, because that's where we saw the bigger need in the machine learning world. So theoretically, there's some opportunities to hook up Hazelcast on the training side, but I would say there are a few things that still need to be done. So I wouldn't advocate going full force into trying to plug it into to improve the training aspect, especially with technologies like notebooks and processes like running on your laptop for a lot of the training, for the model development. So some of the scalability capabilities within Hazelcast might add some overhead to a simplified training environment. So that's something that we're exploring, but for now, most of the focus is on simplifying and improving the speed on the inference side. Do you have any thoughts you want to share on that, Joe?
No, I think you summed it up pretty well. Thank you.
Okay, great. And a couple more questions. What does it mean to use IMAP as a source?
Yeah, that's a comment on that. Yeah, actually, that's exactly what I was talking about previously, about the ability to store data in memory. So IMAP is as you may or may not know, is a distributed in-memory data structure that's partitioned. You can load or write your response or the results of your job to an IMAP for fast access from an online application, or you can actually use IMAP as a source. So as IMAP is, let's say you have a online store and you're putting your transactions in online, our IMAPs have the ability to journal any changes. And so the journal becomes a real-time event stream for a Jet job. So using an IMAP as a source works well for people who are currently using an IMDG to store, maybe it's real-time trades for historical purposes. And as they come into that IMAP, we can read the trades and do certain kind of aggregation or whatever ML, AI processing you want in those events.
Okay, great, thanks. And so the person that asked about the scale flux added a comment, so I appreciate that, that you had done some performance testing on scale flux versus Octane using the YCSB benchmark. And okay, yeah, we'll definitely look into that. And I'm guessing now that you use scale flux as the persistent storage mechanism versus the context of what we're using where it's a RAM alternative. I think that's the difference. So that's something that we'll have to explore.
So yeah, I want to thank both Dale and Joe for such a great presentation. And thanks everyone for taking the time out of your days to join us for today's webinar. We will be sending out an email with a link to the recording, as well as links to the resources that were shared on today's webinar. I did put the link to the online training center for that stream processing essentials in the chat window, but we will be including that in the follow-up email as well. Someone will be reaching out to you after the webinar to help answer any additional questions you may have, as well as Dale said, the questions that we were not able to get to today. So thank you again for joining us, and we hope everybody has a great day.